We want to now try to find the energy stored in an inductor. So let's go back to the equation, the loop equation we got in the previous file, and let's look at this loop equation in more detail. So if we just bring the EMF on one side and IR and LdI by dt on the other, we get this equation. Now, if you look at this equation and you multiply both sides by the current, so if you multiply by the current, what is the physical meaning of each one of these terms? Well, the EMF times the current, that's the rate at which the battery supplies energy to the circuit. I squared times R is the rate at which energy is lost in the resistor. So what then do you think would the meaning of this term be? Well, the principle of conservation of energy says that if the battery is supplying energy to the circuit and some of this energy is being lost in the resistor, that means there must be some energy also being stored in the inductor. And so this term would be the rate at which energy is being delivered to the inductor. So we have now an expression for the rate at which the energy is being delivered to the inductor. And how then could we find an expression for the energy in the inductor itself? So if we integrate both sides with respect to time, what does each term become? This term becomes integration from u initial to u final du, and this one becomes, the inductance goes out of the integration because the inductance doesn't depend, it's a dependence only on the geometry. And so you get integration of I di from the initial current to the final current. This integration is I squared over 2, and then you substitute the upper and lower limits, and you have u final minus u initial. Now, if you start at time 0, the energy in the inductor is 0. The current in the circuit is also 0. And you can show that the current is 0 by solving this RL circuit equation, and you can show that the current at time 0 is equal to 0. So there's no energy stored in the inductor at time 0. So that means that the energy at some later time is 1/2 L times the current squared. And so we have a general relationship now for the energy stored in the inductor at some time t. It's 1/2 L I squared. At time 0, the energy is 0. And as time goes on, as the current increases, the energy stored in the inductor increases.